Welcome to Biogas Basics, a series about the engineering aspects of a biogas plant. My name is Jürgen Kube, and in this presentation, I discuss how feedstocks are characterized and what parameters are required to describe them. I will introduce the term average digestate as the residual of feedstock minus biogas and explain why it is important. We will see that feedstocks with equal biomethane yield are not necessarily exchangeable in a digester diet. Lastly, I will show how to calculate the nitrogen mineralization degree, which can be used to identify feedstocks that can cause ammonia inhibition. Feedstocks for AD plants are characterized by the following properties. Fresh matter, or FM. This is the mass of feedstock going into the digester. Total solids, or TS. This is the ratio of dry matter, a mass, and fresh matter. Total solids is a mass percentage in kilogram per kilogram. TS is measured by drying a sample at moderate temperatures, typically 105 degrees Celsius, until its weight is constant. Loss on ignition, or LOI. The loss on ignition is the ratio of organic dry matter to dry matter. It is measured by incinerating a sample in a furnace at 550 degrees Celsius for 2 hours. Loss of ignition is a weight percentage. The product of loss of ignition and total solids is called volatile solids. It is the ratio of organic dry matter and fresh matter and is a weight percentage. Biogas yield and biogas potential. The biogas potential is the maximal amount of biogas that can be produced per mass of feedstock, for example in a reactor with infinite residence time. The biogas yield is the amount of biogas that is produced in a reactor with limited residence time. The conversion factor is the ratio of biogas yield to biogas potential. The biogas yield is what is observed in real reactors, and the biogas potential requires assumptions on how much biogas can be produced if there were no kinetic or thermodynamic restrictions on the conversion. Biogas yields and biogas potential can be given as amount of biogas per mass of fresh matter, dry matter, or organic dry matter. The preferred notation is in amount of biogas per mass of organic dry matter. Within certain limitations, this is a substrate property. For example, take a starch solution. The organic dry matter-based biogas yield is always the same, regardless of whether the starch is in a 10% solution or in its dry form. But the fresh matter-related biogas yield will vary with the starch concentration. The methane content of the biogas is obviously important. It has an impact on how much methane the substrate produces. It also impacts the density of the produced biogas. CO2 has a much higher density than methane. 1.96 kg per cubic meter for CO2 versus 0.71 kg per cubic meter for methane. When two feedstocks with similar gas yields but different methane contents are digested, the feedstock with the lower methane content will convert more dry matter into biogas because the produced biogas will have a higher density. The product of biogas potential and methane content is called biomethane potential, or BMP. Again, it can be stated related to fresh matter, dry matter, and organic dry matter, and only the latter is a true feedstock property. The methane content of produced biogas depends on the stoichiometry of the substrate. I have a whole presentation about the Buswell formula and the stoichiometry of the biogas process. When a feedstock is digested and converted into biogas, it undergoes the hydrolysis step. Hydrolysis means cutting with water, and water is incorporated into the reaction products. It is used to open up glycosidic and peptide bonds, and is also required in the beta oxidation of fats. As a result, the produced biomass weighs more than the organic dry matter that is digested. The ratio of biogas mass from water to total biogas mass is the hydrolysis water content W height. It can be estimated from the stoichiometry of the digested substrate. See my presentation on the stoichiometry of the biogas process for more details. If this parameter is ignored, the total solid of the produced digestate is underestimated, which can lead to undersized mixing technology and digesters. These parameters are the absolute minimum parameters required to balance a biogas plant, its different reactors, and estimate biogas and digestate production and composition. In the classical mass balance, dry matter is everything in the sample that is not water, but it is measured by drying the sample. The sample can contain volatile components, for example volatile fatty acids, alcohols, aldehydes, or ketones that partially or completely evaporate in the drying process, leading to a false measurement of dry matter and organic dry matter content in the sample. There are some workarounds to include these volatile components, but I do not use them here as the concentration of these components is usually small in solid feedstocks and can be captured with COD measurements in liquid feedstocks. The total nitrogen content is typically given in mass nitrogen per mass of dry matter. In the AD process, nitrogen is incorporated into microbial biomass and converted to ammonia and ammonium. The former is toxic to acetoclastic methanogens. If feedstocks are rich in nitrogen, Organic and inorganic nitrogen should be balanced to assess if ammonia inhibition can occur. Further, feedstock can be analyzed via photoanalysis or elemental composition. This will give information about how much soluble and insoluble fiber, carbohydrates, proteins, and fats are in the feedstock. A biogas batch test will show how fast biogas is produced. The degradation kinetics of the feedstock are important for determining dilution requirements of the plant. A slowly degrading feedstock will only be converted partially into biogas in the first reactor stages, which will lead to high total solids in the respective digester and increased dilution demand. A feedstock might miss some macro or micronutrients, or it might have a high sulfur content which will require extensive desulfurization of the biogas. A lack of micronutrients can easily be overcome by adding trace element solutions. A high concentration of sulfur in the feedstock will require the integration of desulfurization technology in the design process of the plant. Feedstocks can also be assessed by total suspended solids and the chemical oxygen demand, or COD. These parameters are usually used in wastewater applications, liquid feedstocks, or diluted systems. Total suspended solids, or TSS, are measured by filtering a sample over a 0.22 or 0.45 micrometer filter and dry the filter to constant weight. If the sample contains a lot of fibers, the filter blocks very quickly, which means that TSS measurements are usually confined to wastewater streams. COD measurements can give information about the maximal biomethane potential of a substrate. 1 ton of COD can produce up to 350 cubic meter of methane at 0 degrees Celsius and 1 atmosphere. However, this is the theoretical maximum, and in reality, the biomethane yield is less as some of the energy in the feedstock is required for biomass buildup, substrate transport, and maintenance metabolism. This slide shows the Excel formula to calculate average feedstock properties. The feedstocks are characterized by fresh matter, Fm in tons per day, total solids, Ts in loss on ignition, LOI as mass percentage, the biogas potential Y-pot in norm cubic meter per ton of organic dry matter, the methane content and hydrolysis water demand of the produced biogas W height, the density of the biogas ρ, and the total nitrogen content Tn in kilograms nitrogen per kilogram dry matter. Norm cubic meter refers to a reference state of 0 degrees Celsius and 1.01325 bar, a reference state that is commonly used in Western Europe. Make sure you use the correct reference state when designing a biogas plant. Now I add a couple of feedstocks. First, maize silage, a common energy crops used in AD, cattle manure, a liquid feedstock, milled straw, a very dry solid feedstock, whey permeate, a liquid feedstock again, and lastly chicken muck from broiler production. The fresh matter can simply be added up to get the total feedstock demand. The total solids of the feedstock mix is the fresh matter weighted average. It is the sum product of fresh matter and total solids divided by the total fresh matter. The loss on ignition is the sum product of fresh matter, total solids, and loss on ignition divided by the total fresh matter and the total solids of the feedstock mix. The biogas potential is the sum product of fresh matter, total solids, loss on ignition, and biogas potential divided by the total fresh matter and average total solids and loss on ignition. The methane content of the feedstock mix is the sum product of fresh matter, total solids, loss on ignition, biogas potential, and methane content divided by the total fresh matter and average total solid, loss on ignition, and biogas potential. The density of the produced biogas is calculated from the methane content using the ideal gas law. It is the average molar weight of the biogas divided by 22.414 liter per mole. This constant is for the reference state of 0 degrees Celsius and 1 atmosphere and must be recalculated for other reference states using the ideal gas law. The average molar weight of the produced biogas is 16 gram per mole for methane and 44 gram per mole for CO2, which is the remainder of the produced biogas. The hydrolysis water demand is calculated in a slightly different way. It is weighted by the mass of the produced biogas. It is the sum product of fresh matter, total solids, loss on ignition, hydrolysis water demand, and density of the biogas divided by the total fresh matter and average total solids, loss on ignition, biogas potential, and density of the produced biogas. Lastly, the total nitrogen content of the feedstock mix is the dry matter weighted average. It is the sum product of fresh matter, total solids, total nitrogen divided by the total fresh matter, and average total solids of the feedstock mix. The feedstock composition can be used to calculate the overall mass balance of the biogas plant. Fresh matter is water plus dry matter. Dry matter is organic dry matter plus ash. Organic dry matter is substrate plus inert organic dry matter. Substrate plus water reacts to biogas and biomass. So, substrate is the degradable part of the organic dry matter. The rest is inert organic dry matter. Not all the mass of biogas comes from substrate. Some of it comes from the water incorporated in the hydrolysis step. Not all the substrate is converted into biogas. Some is converted into microbial biomass. Biogas is organic dry matter times biogas yield. In cubic meter biogas at the reference state, per ton of organic dry matter times the biogas density. Biomass is the yield coefficient YXS times substrate. And the mass of water used in the hydrolysis is the hydrolysis water demand W height, a mass percentage, times the biogas mass. Putting it all together, we get the definition of substrate as the mass of biogas times 1 minus hydrolysis water demand over 1 minus microbial yield coefficient. Let's visualize this. We take an example feedstock with 30% total solids, 90% loss on ignition, a biogas potential of 650 norm cubic meter per ton of organic dry matter. The produced biogas has a density of 1.3 kilograms per cubic meter at reference conditions. The hydrolysis water demand is 10%, and the microbial yield coefficient is 8%. Further, we define a substrate conversion factor, ATS, of 80%, meaning that 80% of the substrate is converted to biogas and biomass, and 20% remains in the digestate and can be converted in following reactors. We have 100 kilograms of sample. 70 kilograms of the sample are water. 30 kilograms are dry matter. We can split the dry matter further. 27 kilograms of the sample are organic dry matter, 3 kilograms are ash. Of the 27 kilograms organic dry matter, 23.3 kilograms are substrate and 4.7 kilograms are inert organic dry matter. Now 80% of the substrate is converted. Substrate plus water reacts to biogas and biomass. Here 18.3 kilograms biogas and 1.4 kilograms of biomass are produced from 17.8 kilograms of substrate. The remainder of 4.5 kilograms of substrate is still undigested. The water content of the sample drops from 70 kilograms to 68.2 kilograms. 1.8 kilograms are used in the hydrolysis phase and are incorporated into the biogas and biomass. In the next step, we remove the biogas from the digestate and add up the biomass, undigested substrate, and inert organic dry matter to the total organic dry matter in the sample, 10.6 kilograms. The water and inorganic dry matter in the sample remain unchanged. The total solids of the digestate is 16.6%. Its loss of ignition is 78%. We can now define conversion factors for fresh matter, dry matter, and organic dry matter. The conversion factor of the fresh matter is the ingoing minus the outgoing fresh matter divided by the ingoing fresh matter, or 1 minus the ratio of the outgoing to ingoing fresh matter. The conversion factor for dry matter is 1 minus the ratio of the outgoing to ingoing dry matter. And the conversion factor for organic dry matter is 1 minus the ratio of the outgoing organic dry matter divided by the ingoing organic dry matter. The numbers are 16.8%, 47.7%, and 59.7% respectively. These are the amounts of the fresh matter, dry matter, and organic dry matter converted to biogas. Sometimes the conversion ratios are defined as the ratio of total solids or volatile solids instead, like 1 minus Ts out over Tsn. This is only valid in diluted systems when the ingoing and outgoing streams are identical, which is a very rare case in the AD industry and should only be used in wastewater fermentations. In all other applications, the ratio of mass flows must be used. And lastly, with a bit of algebra, we can directly calculate the total solids and loss of ignition of the digestate from the feedstock properties and substrate conversion factor. Just make sure that the units add up, the density terms are in kilogram per ton, and the other terms in mass percentage, i.e. ton per ton. Now let's examine the impact of the conversion factors. We start with the same sample consisting of water and dry matter, or water, organic dry matter, and ash. We then convert 80% of the substrate into biogas. The result is that 100 kilograms of sample react to 68.2 kilograms of water, 18.3 kilograms of biogas, 1.4 kilograms of biomass, 4.5 kilograms of undigested substrate, 4.7 kilograms of inert organic dry matter, and 3 kilograms of ash. What would happen if the substrate conversion is increased from 80% to 100%? More water is consumed, more biogas and more biomass are produced. The sample would no longer contain any undigested substrate, but it would still contain some inert organic dry matter. Now we can increase the biogas yield until all organic dry matter is converted. The sample would consist of 67.2 kilograms of water, 27.6 kilograms of biogas, 2.2 kilograms of biomass, and 3 kilograms of ash. We notice that there is an upper limit to the biogas yield when all organic dry matter in the feedstock is converted. The resulting digestate would still contain some organic dry matter in the form of microbial biomass. we can calculate the upper limit of a biogas potential. It is the inverse biogas density times 1 minus microbial yield coefficient over 1 minus hydrolysis water demand. This formula is very handy. When feedstocks are used that degrade completely, for example food soup, fats, oil, greases, sugar solutions, glycerol, or similar feedstocks, the biogas composition and subsequent biogas density is easy to measure, much easier than the actual biogas yield. The microbial yield coefficient is a constant, around 8%, and the hydrolysis water demand is known from the stoichiometry of the feedstock. This formula can also be used as a sense check to spot unrealistically high biogas yields. If the yield is higher than the inverse density, alarm bells should be ringing. A very common mistake during the design phase of an AD plant is to select feedstock purely based on their costs and fresh matter biomethane yield, while overlooking other properties like total solids, specific biogas yield, and methane content. Let's compare 4 feedstocks with the same fresh matter-based biomethane yield per ton. All feedstocks make 115 cubic meters of methane per ton. Can they be replaced like for like in a digester diet? Well, the answer is no. Let's start with straw. This is extruded straw and has been premixed with water to bring the TS down to 45%. Normally, dry straw has close to 90% TS, but can get wetter when top or side bales are used. The loss on ignition is 89.7%. The biogas potential is 570 cubic meters per ton of organic dry matter, which is typical for extruded straw. Biogas is made almost exclusively from cellulose, which means the produced biogas has a 50% methane content. The water demand of the hydrolysis is 5%. If we would use the classical Boswell formula, it would be 10% for cellulose, but when we consider biomass buildup, the water demand drops to around 5%. See my presentation on the stoichiometry of the biogas process for more details. 100 kilograms of straw would degrade to 30.8 kilograms of biogas, 53.5 kilograms of water, 2.5 kilograms of biomass, 8.6 kilograms of dry matter would be inert organic dry matter, mostly lignin and cellulose covered by lignin. 4.6 kilograms would be ash. Chicken muck is usually a cheap feedstock and looks like a good feedstock in an Excel table. Chicken muck comes in 2 qualities: broiler muck from meat production and layer muck from egg production, which is far worse than broiler muck. Dried layer muck has around 55% total solids and 76% loss on ignition. Layer muck contains grit, which is fed to the chicken to improve eggshell production. Around a quarter of the dry matter is ash, salt, and grit. The biogas potential of chicken muck is around 500 cubic meter per ton of organic dry matter. Chicken muck contains protein. The methane content is typically higher compared to carbohydrates. We ignore the nitrogen content and ammonia toxicity in this comparison, but the high nitrogen content of chicken muck leads to a higher pH in the digestate, which will then lead to a higher methane content in the biogas, as more CO2 is stored in the digestate as bicarbonate. So, the methane is 55% compared to the 50% for straw. The protein content will also lead to a higher hydrolysis water demand, 12% instead of 5% for straw. Because of the higher methane content in the biogas, the density of the produced biogas is slightly lower compared to the biogas from straw. 100 kilograms of chicken litter degrade to 26.7 kilograms of biogas, 41.8 kilograms of water, 2 kilograms of biomass, 16.3 kilograms of inert organic dry matter, and 13.2 kilograms of ash, which also contains the grit. Maize silage is a very common feedstock for energy crop-fed AD plants. We can see why it is the preferable energy crop in AD when we look at the degradation. It has 32% total solids. Almost all of the dry matter is organic. The loss on ignition is 96%. The specific gas yield is quite high, 720 cubic meters per ton of organic dry matter. The methane content is low, 52%. The hydrolysis water demand is also low, around 5%. 100 kilograms of maize silage degrades to 29 kilograms of biogas, 66.5 kilograms of water, 2.4 kilograms of microbial biomass, only 0.7 kilograms of inert organic dry matter, and 1.3 kilograms of ash. The last feedstock is food soup. The TS is 24%. The loss on ignition is 89.5%. The biogas potential is 892 cubic meters per ton of organic dry matter. The methane content is 60%. Food soup contains fat and protein, which also leads to a higher hydrolysis water demand of 15%. Because of the high methane content, the density of the produced biogas is the lowest of all in the table. 100 kilograms of food soup degrade to 23.3 kilograms of biogas, 72.5 kilograms of water, 1.7 kilograms of biomass, and 2.5 kilograms of ash and salt. Note that the organic dry matter in the food soup degrades completely. There's no inert organic dry matter in the digestate, only microbial biomass. We can now remove the biogas and calculate the total solids of each of the 4 digestates. The straw creates a digestate with 21.5% total solids, and the chicken muck creates a digestate with 44.4% total solids. Typically, digesters for these feedstocks operate somewhere in the region between 8 and 15% total solids, so both feedstocks would require significant dilution with water or process water. I will talk more about dilution water requirements in the mass balance mini-series. Maize silage, on the other hand, creates a digestate of only 5.7% total solids. This digestate can easily be stirred in the digester and does not require dilution. Food soup has a 100% organic dry matter conversion and creates a digestate with only 4.2% total solids. And these solids are salt, ash, and microbial biomass. There's nothing left in the digestate that can cause higher viscosity. We can go one step further and calculate the concentration of inert organic dry matter and undigested substrate in the digestate. We can call this parameter fibrous solids, which is a good indicator of defining an upper limit of the solids a digester can handle. The digestate from extruded straw digestion contains around 12% fibrous solids, and the digestate from chicken muck 22%. Compare this to the digestate from maize, which contains only 1% fibrous solids. From the perspective of fibers in the digester, straw is 12 times and chicken muck 22 times worse than maize. So, we can see that feedstock cannot simply be replaced like for like when it comes to biomethane potential. We will also have to address the viscosity of the produced digestate, or as a proxy, the total solids or fibrous solids content. On top of this, there are also plenty properties that cannot be quantified. For example, the impurities content in food soup, the nitrogen and grit content in chicken muck, the need for pasteurization or special regulation regarding waste or animal byproducts. Generally, I would aim for feedstock with a high organic dry matter specific biogas potential. This ensures that most of the organic dry matter is converted into biogas and does not stay in the digestate as inert fiber and requires mixing. However, the specific biogas potential is not the only parameter. It must be assessed together with the density of the biogas and the hydrolysis water demand. Organic nitrogen in the feedstock will be reduced to ammonia and partially taken up by the microorganisms of the AD process. Ammonia is toxic for acetoclastic methanogens. See my mini-series about microbial growth for more information. So, let's have a look at the fate of nitrogen in the digester. We start again with the terminology. Organic nitrogen is nitrogen in the biomass plus total ammonia nitrogen plus inert nitrogen. Total ammonia nitrogen, or NH4N, is the sum of ammonia and ammonium. We know from a previous slide that biomass is microbial yield coefficient YXS times biogas mass times 1 minus hydrolysis water demand over 1 minus YXS. We can multiply this formula with the nitrogen content of microbial biomass, which is around 10 mass% for anaerobic biomass. We now make an assumption that the conversion of organic nitrogen to total ammonia nitrogen and nitrogen bound in microbial biomass is the same as the organic dry matter conversion. The degree of nitrogen mineralization is the ratio of produced total ammonia nitrogen to organic nitrogen in the feedstock. With a bit of algebra, we can finally calculate the nitrogen mineralization degree as a function of feedstock properties. The formula is shown here. The nitrogen mineralization degree is important when using nitrogen-rich feedstocks and can be used to estimate the concentration of total ammonia in the digester and the potential dilution requirement. At this point, I must address another biogas myth, the CN ratio. Unfortunately, many textbooks and publications use the CN ratio to estimate if a nitrogen inhibition occurs. They give certain windows, somewhere between 1 to 20 to 1 to 40, though do not state whether this is a mass or mole ratio. Like many biogas myths, the underlying idea comes from aerobic wastewater treatment. Aerobic microorganisms have a much higher microbial biomass yield than anaerobes. Aerobic microorganisms make 0.3 to 0.5 kilograms of biomass per kilogram of substrate consumed. Anaerobic microorganisms make 0.03 to 0.1 kilograms of biomass per kilogram of substrate consumed. Microbial biomass contains around 10% nitrogen. Most feedstocks contain around 40 to 50% carbon, so there is a certain ratio of nitrogen required per carbon consumed in bioreactors. In aerobic wastewater treatment, the carbon removal can be so high that a carbon source like methanol ethanol, or glycerol must be added in the later stages of an aerobic treatment facility to eliminate nitrogen in the denitrification phase. The CN ratio covers only nitrogen limitation, and because of the much lower yield coefficient of anaerobic microorganisms, an anaerobic reactor needs less nitrogen per mole carbon consumed than an aerobic reactor. Nitrogen toxicity in the AD process cannot be addressed with the CN ratio. Simply adding more carbon to a biogas reactor does not make the nitrogen less toxic. Because of the low yield coefficient, the nitrogen demand for growing anaerobic microbial biomass is quite low. Also, the microorganisms have no way to measure or sense the carbon concentration in a digester, especially when the carbon is not water-soluble. The nitrogen toxicity stems from the concentration of ammonia nitrogen, not from the CN ratio. I talk more about ammonia nitrogen in the mini-series about microbial growth in the episode about methanogens. The way to overcome a nitrogen inhibition is the addition of more nitrogen-free or nitrogen-depleted water, not by adding more carbon. The only way where a CN ratio might be useful is in extreme cases when the feedstock is virtually nitrogen-free, for example in whey-permeate digestion or in anaerobic wastewater treatment. All other feedstocks usually contain more than enough nitrogen to cover the nitrogen demand for microbial growth. So, do not use the CN ratio. Before I conclude, I want to address a couple of important feedstocks and potential pitfalls. I will focus more on quality parameters than quantifiable parameters in this list. First on the list are energy crops. Energy crops are purposely grown plants, harvested and often stored on site of the biogas plant. They digest easily, albeit slowly, and have a high specific gas yield. They produce a relative clean biogas with little contaminations like volatile organic compounds, VOC, or H2S. Digested energy crops still contain some fibers, and the digestate can be separated easily to create a fiber-rich solid digestate. This solid digestate is a valuable and well sought-after fertilizer, particularly useful for reintroducing carbon into carbon-depleted soils. The most used energy crop in AD is maize because of its high specific gas yield and high area yields. Rye, grass, barley are also used in Europe. Generally, an AD plant for digesting energy crops is not very complicated and does not require process steps for impurities removal, desulfurization, ammonia scrubbing, biogas cleaning, odor abatement, water treatment, pasteurization, and other ancillary process steps. Energy crops can face some political headwinds in the food versus fuel debate, especially when grown unsustainable and grown as a monoculture year after year on the same land. But if they are integrated into a larger crop rotation and if sustainable farming methods are used, they can increase the food production from a field. From the economic point of view, energy crops provide the advantage that they can be bought and locked into long-term feedstock supply contracts. However, energy crops have a high cost per cubic meter methane generated. Straw is usually quite dry and has a high fresh matter-specific gas yield, but its organic dry matter-specific gas yield is very low, meaning that it will produce a very dry average digestate. Untreated straw has a low biogas yield and it benefits from a pretreatment including but not limited to milling, pelletizing, briquetting, steam explosion, steam treatment, extrusion, thermal or hot water treatment. Straw is covered in a wax layer which makes it hydrophobic. Untreated straw barely mixes with water or digestate. Straw will always require some external water for dilution. It is not possible to operate a monodigestion of straw and create dilution water from recirculating separated digestate. External water addition is always required. See my mini-series on the mass balance for more details. Straw is usually purchased in bales and commercial straw debaling and milling lines are available. Straw bales can contain stones, which can create high wear and tear in the straw handling lines. Commercial straw handling technology often contains a pneumatic conveying step that removes stones from the feedstock. Straw bales can be stored relatively easily in larger stacks. The top and side bales are exposed to the elements and can start to rot and show a lower gas yield but are cheaper. Large stacks of straw bales can pose a fire risk, for example from lightning strike or arson. Loose straw has a low density, around 50 kilograms per cubic meter, and requires a lot of storage space on site. In some regions, straw is a waste product that stays on the field or is plowed under. In other regions, straw is a sought-after resource. Straw is not an energy crop, which has advantages in some regions where subsidies are linked to feedstock categories like waste, residue, or product. Chicken muck is a very attractive feedstock, at least on paper. It is a waste, it is a manure, it has a high biogas yield per ton of fresh matter, it is nutrient-rich. Chicken muck comes in different forms. When it comes from meat production, it is called broiler muck. When it comes from egg production, it is called layer muck. Broiler muck is far superior to layer muck. Both feedstocks have roughly the same biogas yield per ton of organic dry matter, but egg-producing chickens are fed grit to improve eggshell production, and the grit ends up in the muck and will eventually settle in the digester if not removed prior to feeding. Layer muck also contains eggshells, which are highly abrasive for progressive cavity and rotary lobe pumps. Layer muck is produced continuously, whereas broiler muck is cleaned out after a crop is completed, usually after 7 weeks, and might require some storage facilities. If muck contains bedding residues, it is called chicken litter. Bedding materials can be straw pellets, long straw, wood chips, or sawdust. The presence of bedding material can make a shredding step necessary to break up agglomerates. Chicken muck from chick production is called rearing muck. Chicken muck is rich in nitrogen. Somewhere between 3 and 5% of the dry matter is nitrogen. Around 20% of this nitrogen is in the form of ammonia, and more ammonia is released during the fermentation. Ammonia toxicity and ammonia in the biogas are important features of a plant that is designed to feed a high percentage of chicken muck in its diet. But chicken muck does not only contain nitrogen, but also phosphor. In areas with high phosphate levels, land spreading of digestate from chicken muck fermentation can become difficult. The phosphate and nitrogen can react to struvite and form precipitates in pumps and on heat exchanger surfaces. Chicken muck is rich in sulfur, and desulfurization of the produced biogas is required. Without desulfurization, biogas produced from chicken muck will contain 2,000 to 5,000 parts per million H2S. The high nitrogen content of chicken muck will lead to a high pH in the digester, which leads to a high ammonia content of the produced biogas. A biogas plant that is designed for a high percentage of chicken muck in its diet should scrub ammonia from the biogas prior to using it in a CHP, or biogas upgrader. Solid and liquid pig and cattle manure are traditional feedstocks in AD plants. The first mixing and pumping technologies for AD plants derived from manure handling. Though they do not have a high fresh matter or organic dry matter specific biogas yield, their abundance in certain regions make them a good base feedstock for biogas plants. Liquid manure is often used for dilution of a feedstock mix. Manure is rich in microbial biomass, and manure-fed digesters can operate at very low residence times without acidifying and facing washout phenomena. Manure also contains water and ammonia nitrogen, which makes it a good storage for CO2 in the form of bicarbonate. It also contains micro and macronutrients, though sometimes also antibiotics and non-essential heavy metals. Lately, some countries have increased or coupled biogas subsidies to the use of manure in the feedstock mix. Liquid manure is stored in slurry tanks or lagoons and emits biogas. The idea is to use manure as a feedstock and thus preventing methane emissions from slurry stores. Methane is a strong greenhouse gas. However, we should realize that slurries and manures are byproducts from intensive agriculture. A subsidy for biogas from manure is an indirect subsidy for intensive agriculture. Methane emissions from agriculture are accepted as unavoidable and not the responsibility of the farmers and industries that produce livestock via intensive agriculture. By subsidizing biogas from manure and financing these subsidies via taxes or fees on power, gas or fuel, a vegan taxpayer or customer of a power company would directly support intensive agriculture. It would make far more sense to make anaerobic digestion of manure from intensive agriculture compulsory and remove all subsidies for biogas from manure. Sugar beets are similar to energy crops. They are purpose-grown and must be bought as a feedstock. Sugar beets contain a lot of stones, sand and soil and must be washed and chopped before being fed into an AD plant. This requires special equipment which must be able to handle large amounts of sugar beets in a short period. Sugar beets can be ensiled, though they create a significant amount of leachate, which is very rich in acids and alcohols and has a foul smell and is very corrosive to metal, concrete, asphalt and to the skin. The leachate is created during a short window after ensiling, which might overwhelm the leachate handling system. Sugar beet can also be ensiled alongside other crops, which helps to offset the leachate problem. Sugar beets are lifted from September to March and can stay in the soil or at the field, which can help minimizing the storage requirements. They can also be used as a seasonal feedstock. The biggest advantage of sugar beets is that they degrade quickly and almost completely. Digested sugar beets have a water-like consistency. Any AD plant that dilutes the primary digester to reduce the viscosity can feed sugar beets instead and create more biogas in the same digester volume. The water-like digested sugar beets simply replace the process water for dilution. Sugar beets can also be fed into the secondary digester. Because of their quick conversion, they do not require long residence times. However, the handling requirements and contaminations of sugar beets make them a problematic feedstock. Farmers usually love to supply sugar beets to AD plants, but AD plant operators hate them because of all the problems previously mentioned. Sugar beet pulp is a byproduct from sugar processing. It is the pectin backbone of the sugar beet after the saccharose has been removed from the beet. Sugar beet pulp is a good feedstock for livestock but can also be used in biogas plants. Similar to sugar beets, it degrades fast and almost completely. Pectin is one of a few carbohydrates that produce a biogas with less than 50% methane. The main difference to sugar beets is that the pulp can contain sulfates which are introduced during the processing at the sugar factory. This leads to a higher hydrogen sulfide content of the produced biogas. Old sugar beet pulp can clump together, which can cause problems in AD plants when those agglomerates drop like stones in the digester, especially when the pulp is fed into the digester via an auger system that compacts the sugar beet pulp. Food waste is pre- and post-consumer waste from source-segregated collection called SSO, source-segregated organics, waste from restaurants and cantinas, and packaged waste from supermarkets. Food waste typically requires a pretreatment, a defibering step, followed by a removal of the light fraction or plastics. Heavy fraction, such as larger glass shards, pieces of cutlery, stones, and other impurities that find their way into the waste collection. The defibering is normally done in hammer mills, pulpers, or presses. Mills are relatively cheap and can separate some of the light fraction using pneumatic conveying, but they smash impurities and especially glass to pieces and create a fine grit and plastic fines. Pulpers shear the food waste and leave the light and heavier impurities in larger particle sizes which are easier to remove. Presses do not separate light and heavy fractions and are used if a high selectivity and pure light and heavy fractions are not required. The output from the processing step is called food soup or pulp. It should undergo a degritting step before it is fed into a biogas fermenter. In some countries with established AD infrastructure and high subsidies like the UK and the Netherlands, commercial waste handlers aggregate several waste fractions with the aim to produce a food soup with constant properties and sell the produced food soup to biogas plants. If the quality of food soup is not constant, it is sold on a chemical oxygen demand or COD basis. 1 ton of COD can generate up to 350 norm cubic meter of methane, though this is the upper limit and not a guaranteed conversion factor. The main attributes of food soup is the COD, the concentration of grit, plastic fines, and the presence of chloride, sulfate, or sharp objects. Glycerin or glycerol is a byproduct of the biodiesel industry. It converts almost instantly into biogas when fed into a biogas reactor and is a great booster feedstock which can be used to control biogas production. For example, glycerin feeding can be controlled by the gas storage level. Feeding starts when the gas storage drops below 50% and it stops when the gas storage is at 60%. This simple control loop ensures that there is always enough biogas in the storage to run the gas consumers flat out. The almost instant gas production can pose a danger to a biogas plant if a truckload of glycerin is fed into the plant within a short period. The AD plant might make so much biogas that it overloads the gas system and take the roof off. Best practice is to keep glycerin in separate storage tanks and feed it with a small designated glycerin pump through a small pipeline into the digesters. It can be fed into a post-digester or even storage tank because it reacts so quickly. Glycerin comes in 2 qualities: industrial grade at around 20% water content and farmer grade. Industrial grade might contain fossil methanol and rests of the catalyst like sodium hydroxide or sulfuric acid. In the latter case, the biogas reactor will also produce large amounts of H2S. The fossil nature of methanol might cause problems in some subsidy schemes. Farmer-grade glycerin is pure rocket fuel, but it is more expensive. It solidifies at 18 degrees Celsius and must be kept in heated tanks or diluted with a little bit of water. Adding water to glycerin lowers its melting point. A mixture of 2 parts glycerin and 1 part water by mass has a freezing point of minus 46 degrees Celsius. It also might not count as waste or byproduct in some jurisdictions, which has implications on the eligibility of subsidies. Whey permeate is a waste product from creameries. It is an aqueous lactose solution with around 7 to 10% total solids and is produced when milk protein is removed from the whey by ultrafiltration. It can be evaporated to produce a fodder or fed into a biogas plant. Whey permeate is one of the few feedstocks that lack nitrogen, and a source of nitrogen must be added to the fermentation. Whey permeate will produce less than the theoretical maximal methane yield based on COD. 1/8 of the energy in the lactose is used by the active transport mechanism, the ATP binding cassette or ABC transporter. that transports the lactose into the cell. COD yields are around 280 cubic meters per ton. COD. Fresh whey permeate is acidic, and when it is stored in tanks, it will further acidify to lactic acid. Lactic acid is converted to biogas via propionic acid, which is toxic to acetoclastic methanogens. Preferably, whey permeate is fed fresh into a biogas reactor. This can be achieved by using 2 storage tanks and empty one completely before refilling it. If the tank always operates half full, it will establish a hydrolyzing biology of lactic acid bacteria. Whey permeate also contains calcium and phosphate, which can precipitate as dicalcium phosphate in the storage tanks and creates a cement-like mineral sludge. Good mixing is required in the storage tanks. Whey permeate contains residues of cleaning in places fluids, like sodium hydroxide, hydrochloric, or sulfuric acid. The acid anions can cause problems in the digester and downstream effluent treatment. High-strength wastewater streams are normally treated in bespoke reactors, especially if they are free of suspended solids. They are characterized by a high hydraulic and low organic load and are digested in reactors that separate hydraulic from solid residence time by means of biomass retention. The most common reactor for this is the upflow anaerobic sludge blanket, or UASB reactor, but there are several other reactor forms. High-strength wastewater often displays a high methane content because much of the produced CO2 leaves the biogas reactor via the digestate as dissolved CO2, bicarbonate or carbonate. The wastewater can lack micro and macronutrients such as phosphate and nitrogen, and dosing might be necessary. Especially if the wastewater comes from a distillation or filtration step, it might be sterile or characterized by low microbial biomass concentrations. If this is the case, and the reactor acidifies, it will need fresh seeding material as inoculum to restart the process. Some reactors rely on granulating biomass, which will form large agglomerates of biomass, stabilized by calcium carbonate and other mineral precipitates. These reactors are often inoculated with granulated sludge from other wastewater reactors, but this sludge will also form if the reactor is inoculated with a rich inoculum from a different source. However, the water will require some calcium or magnesium to form the mineral structure of the granule. High-strength wastewater should not be combined with fibrous feedstocks, meaning that high hydraulic freights should not be combined with high organic freights. It is better to digest the wastewater in a separate bespoke wastewater digester and the fibrous feedstock in the CSTR, and combine the biogas but keep the effluents apart. A mixed feedstock would require a high residence time for the fibers for the high volume flow of the wastewater. Even if there are some techniques to separate the fibers from the water after the digester, like a dissolved air flotation or a vibration screen, it will require a lot of coagulant and flocculants to separate the fibers from water. Sewage sludge is a mixture of primary sludge and secondary sludge from a sewage treatment facility. The primary sludge is the solids that can be filtered or separated from the incoming wastewater. The secondary sludge is the aerobic biomass that is created in the aerobic contact process that cleans the wastewater by converting dissolved BOD into biomass and CO2. Sewage sludge digestion is one of the oldest commercial biogas applications. It was first introduced not to generate energy, but to reduce the sewage sludge volume, which is a major cost position for a sewage treatment plant. Aerobic biomass has a high yield coefficient of 0.3 to 0.5 kilograms biomass produced per kilogram substrate consumed, whereas anaerobic biomass has a yield coefficient of only 0.05 to 0.1 kilograms biomass created per kilogram of substrate consumed. The substrate in this case being the aerobic biomass created. Sewage sludge has a TS of only a few percent, and sewage sludge digesters are generally designed for low viscosity. Some digesters have the typical egg-shaped form. The residence time in those digesters is not too high, usually around 20 days. The conversion efficiency does not really matter, and the hydraulic freight is high, so longer residence times will require large digesters. However, the sewage sludge production can show seasonal variations, and the digesters are not designed for efficiency, but so that they never fail. Some plants try to boost the gas output by combining sewage sludge fermentation with food waste fermentation, especially if the food waste is collected by the same entity that runs the sewage treatment facility, and this can provide benefits to the process, but sewage sludge should not be combined with fibrous waste that would require longer residence times and create a solid digestate, which would have to be treated like sewage sludge. Because sewage sludge is mostly aerobic biomass, it benefits from a pretreatment that breaks open the cells. This pretreatment can be a ball mill, high-pressure homogenization, ultrasound, or steam explosion treatment. The resulting digestate from sewage sludge digestion attracts heightened scrutiny from authorities, and solid residues must be incinerated in most jurisdictions. Let's conclude. Feedstocks are characterized by fresh matter, total solids, loss on ignition, biogas potential, methane content, hydrolysis water demand, and total nitrogen. A simple mass balance over the digestion step gives the average digestate. The TS of the average digestate is an important parameter in the design of an AD plant. It will give the amount of solid and liquid digestate that can be produced and tell if the digester will require external dilution water. Different feedstocks with the same fresh matter biogas or methane yield are not automatically exchangeable in a diet. They have different digestate composition and will require different amounts of internal or external dilution. Look for high organic dry matter specific biogas yields to select preferable feedstocks. Organic nitrogen in the feedstock will be converted to ammonia and ammonium during the digestion. The mineralisation degree can be calculated from the organic dry matter conversion, biomass yield coefficient, and total nitrogen content of the feedstock. With that, the ammonia concentration in the digestate can be calculated, which determines the nitrogen toxicity. Do not use the CN ratio for predicting nitrogen inhibition. Adding more carbon to the digester does not reduce the toxicity of ammonia. In fact, the only way to overcome nitrogen inhibition is dilution with water, not carbon. The CN ratio should only be used in cases of nitrogen limitation, but even then, the nitrogen mineralization degree and the limitation kinetics is more accurate than the CN ratio. In addition to the quantitative parameters shown here, many feedstocks have distinct properties that must be considered in the selection of a diet of a biogas digester. Not every possible feedstock can be listed here, but many of their potential problems of feedstock mixes can be foreseen with some experience or common sense. This concludes the presentation about the properties and exchangeability of biogas feedstocks. I hope you learned something new, and I see you in the next episode about biogas basics.